All right, I'm starting. All right, good morning, everybody. Welcome to another exciting morning of chemistry with your host, me, Dr. White. I hope you're all going to have a great day. Sun's out. Dr. White feels good. Had a great time since we last met. Did a lot of yard work and a whole lot of other stuff. But let's get on to chemistry. All right, couple of things. First of all, and I've got to get myself in gear because I'm too used to teaching in a classroom, just saying it there. I've got to send out emails. But this Thursday, I will go through problem set for chapter 6. So I hope you all work on that before I do that. And I'll do that Thursday, first thing. Also, I posted it. The lab that we'll be looking at on Thursday, I've already posted in Blackboard. Don't forget the lab we did last Thursday is due this Thursday. I like those hand signals. I'm getting better at that. Not. But anyways, this Thursday, the lab we did last week is due. Please hand in labs. They're easy points for you. You don't want to miss points by not handing in labs. So hand in your labs, please, everybody. All right. Last week, I was talking about balanced chemical equations, and there are a few more things I want to show you. And I'm going to ask my thumbs up people because yesterday I had technical problems up the yin yang. I mean, a lot of them I finally fought through and fixed, but everybody see my whiteboard? Give me a thumbs up. Thank you. All right. Just to remind you, when you have a balanced chemical equation, you have the same number of atoms of each type on each side of the arrow. Remember, let's do a quick review. This is a chemical equation. This tells you that A plus B makes C and D. At the base of the arrow are the reactants. That's an S, which I'm more likely to call starting materials. At the head of the arrow are always the products, or product if there's only one. And both industry and academics use at the head products, but at the tail, those are the reactants. That's more academic. If you work in the chemical industry, which Dr. White did for many decades, we call that starting material. Now, if we look at here, the reactants are hydrogen gas, oxygen gas making water. And if it's balanced, there should be the same number of atoms and same type on each side. Here I have two, here I have two. Ooh, two oxygen, one. Now, you can't change these numbers in a formula, but you can change the number in front, which we call the coefficient. Hopefully I spelled that right. Did I tell you I was always the first one down in spelling bee? Other than organic stuff, I can't spell worth a dime, worth anything. And when we're in a classroom, I've yet to find a button for the whiteboard spell check. But anyways, how do we balance this? This side has 2 oxygen. I'm putting the dash there so you know it's not number 20. How do I get this side? You change the coefficient. Now I have 2 oxygen on this side, but 2 times 2 is 4 hydrogen. Oh, look, I only have 2 on this side. How do I make it 4? Put a 2 there. And now we have 4 hydrogen. 4 hydrogen, 4 hydrogen. 2 oxygen, 2 oxygen. This is balanced. And remember last week I gave you some tips. and one of those was do hydrogen, oxygen last. Let's try one. Why don't you try one? I might have given it to you, but if you don't remember, try again. Oh, another thing, it doesn't matter which goes first. I could have just easily put the water first and the CO2 carbon dioxide last. So why don't you try this? Why don't you try and balance it? See what a nice guy I am? I share. Remember, do hydrogen, oxygen last. Makes your life so much easier and you get it a lot quicker to the correct answer. And when you're done, give me a thumbs up, or if your video is on, you can also smile. If we were in a class, I'd be looking around, I could tell when people are done. But online, since I don't have X-ray vision, I can't. Or telescopic vision, I guess would be the better thing. Or internet telescopic vision. Uh-oh, it's evolving into pretty bad humor Tuesday. I'll try and put a cap on it. All right, anybody need more time? I'll give you another 15 seconds. Go. All right, time's up. Let's get to work. Now, you notice 5 carbon, 1 carbon. That's not balanced. And I should also mention on test 2, there's going to be probably 4 equations you have to balance, usually 3 points each. That's 12 points out of 100 points. So this is an important topic. If I ask you to balance an equation on a test, you're going to have to balance it. The answer, it's already balanced, will never, ever be correct on a test of mine or the final. All right, so if I have 5 carbon here, how do I get 5 carbon here? Put a 5 in there. That was hard. Now, all I have left is oxygen and hydrogen, and I'm going this way, so I'll do the hydrogen. I have 12 hydrogen. Ooh, I only have 2. How do I get this to 12? Well, 2 goes into 12. Get your calculator out 6 times. Luckily, they still taught the math tables, multiplication division tables when I was in grade school. So I now have 6 times 2, that's 12 hydrogen. Next, here I have 2 hydrogen. How many on this side? You count all the, oxygen. You count all the oxygen in all the molecules on the product side. So 5 times 2 is 10 oxygen plus 6 times 1 is 6 oxygen. Add them together, that's 16 oxygen. I only have 2. 2 goes into 16 8 times, and I have 2 times 8 times 2, 16 oxygen. Now, before I go on to the next problem, I'm going to check that I do it right. 5 carbon, 5 carbon, 12 hydrogen, 12 hydrogen. Oh, look, we did. 16 oxygen, 16 oxygen. Now, on a test, all you'd have to do is put the 8, 5, and 6 in there. But I'll be honest with you, I always do this, so I make sure I didn't make a mistake. public service announcement, 2 of them from Dr. White. 1, by the time I finished my PhD, got my PhD, I did more tests and harder tests than you've ever taken so far. One of the things I learned early on is the more I let the paper do the thinking, the better I did. How do you make paper do thinking? You write down things on the paper instead of keeping it in your head, and it makes your life much better. As you see here, I wrote these underneath. Yes, I could have said, well, I got 5, that's done. But this writing it down, same thing with other type of problems, makes your life much, much nicer. All right, let's look at a different type of balanced chemical equation. Oh, one other thing I should point out. If you can divide all the coefficients by the same number and get whole numbers, you should. You should never have a multiple. Example would be what instead, which would be balanced in terms of this, but not in terms of the rules for balancing. What if I did this? And you don't have to write this down, but you'd see 10, 10, 24, 24, then 20 plus 12, 32. So it's balanced in terms of atoms, but notice I can divide each one of these by the number 2. And what that brings me back up to is this. If you do this on a test, that's wrong. And I'll mark it wrong. And, well, let me get my red pen out. And wrong. Because if you can divide all the coefficients by the same number and get whole numbers, you should. They should never be a multiple of a number. So it's an important thing because I see this on tests. I'm telling you that, so you don't do that. And this would be the correct way. All right. By the way, I haven't used that in a while, but this means I'm done with this stuff right here. I'm starting something new. Now, here we have iron plus oxygen making ferric oxide, which is also known as rust, which you don't want happening on your car. But the question is this balanced? And you notice over here, I have 1 iron, 2 iron. Well, it's not balanced, but watch closely. This is a special type of balanced chemical equation skill you should have. On this side, I have 2 oxygen. On this side, I have 3 oxygen. And there's no way I can multiply this number 2 by a whole number to get 3. There's no way I can multiply this number by a whole number, not a fraction or a decimal, to get 2. So what do? No, you don't give up. This I call even odd. Because one side is even. I hope you all know what that means. I hope you do. If not, see me after class. And the other side is odd. Well, what do you do with that? Well, you've got to find a way to get them equal. Well, the trick I found, or the method, that sounds more professional, the trick I use, is multiply this number times this number. And they'll both go into that. And what's 2 times 3 is 6. So if I have 6 oxygen on this side, how do I get that? I put the number 3 there. How do I convert this into 6 oxygen? I put the number 2 there. So now I have 6 and 6. Why, that looks, hold on one second. This looks ugly. Now I feel better. And it looks more professional. So I have 6 and 6. Am I done? No, because now I have 4 iron. 2 times 2. How do I get 4 here? Well, that's simple. And that's how you do it. If you don't know that trick, you can spend the next 30, 40 minutes trying to balance it and be very frustrated. But once you see on one side of the arrow, you have an odd number of atoms of one type and the other side even, multiply those two numbers together, and that's what each side should have for that atom. And that makes your life pleasant because you can do it. And here's one for you. If you take potassium perchlorate, by the way, this is solid rocket fuel used by the military. It oxidizes very quickly and gives off a lot of heat and breaks down to give potassium chloride and oxygen. Why don't you balance it? Have fun. Remember, use my trick, even odd. And when you're done, give me a thumbs up. And as always, thank you for coming to the class this morning, even though this is a synchronous class, but hopefully it helps you being here live. I'm live. All right, anybody need more time? Going once, twice, nobody yelling at me, so let's do it. All right, look at the balanced chemical equation. We have 1 potassium, 1 potassium. That looks good. 1 chlorine, 1 chlorine. So far, real good. 3 oxygen, 2 oxygen. Notice this side is odd, this is even. So what do? Multiply the 3 times 2, you get 6. 2 goes into 6 how many times? 3. 3 goes into 6 how many times? 2. So let's take a look at this. I have 2 potassium, 2 chlorine, and 6 oxygen. All I've done is multiply this times the number of atoms in the molecule. On this side, if I look over here, 3 times 2, I have 6 oxygen, looking good, but I only have 1 potassium, 1 chloride. I need 2. So how do I do that? Put a 2 in front. Oh, that's the ugliest looking 2. Let's try and do a better one. That's better. Now Dr. White feels better. So this is how you balance it. And let's see if we did it. On this side, I have 2 potassium. I have 2 potassium on this side. It's good. Here I have 2 chlorine, 2 times 1, 2 chlorine. It's balanced. And finally, I have 6 oxygen, 6 oxygen, success. We did it. And that's how you do even odd. So remember, when one side has an odd atom, number of same atom odd, the other even, what multiply the 2 numbers together and divide each side into that number, and that's the trick to doing that. Now, let's see if you can put everything together I taught you. Remember, leave hydrogen, oxygen last. That's a 4. And have fun. Balance this equation. Let me clean this up a little. There you go. Remember, leave hydrogen, oxygen last. You don't have to, but it makes your life easier. This one's a little tough, but if you follow my advice, you should get to the right place. If not, I'll show you how to do it in a little while. And when you're done, don't forget, give me a thumbs up if you'd like to. If you don't want to, well, that's okay too. Thank you, Vivian. One of these days, I can get a recording and play it like from The Price is Right, which I haven't watched in decades. Dun, 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 dun. Nah. All right, I'll give you a 20-second warning. Warning, 20 seconds, I'm starting again. Fast clock, no. All right, let's take a look at this. All right, if we look at this, is it balanced? I don't know. Well, it's on a test from Dr. White. By the way, it would be 3 points each. Boy, my first or second grade teacher would be nice. Wow, you print pretty good. All right, back to chemistry. 1 iron, 2 iron. Well, how do I get to both sides 2 iron? Simple. I put a 2 there. So now I have 2 iron and 2 iron. Well, that's oxygen. That's hydrogen. Dr. White says wait till last. And good news, I follow my advice, which has been good in life. Hydrogen, I'll leave that to last. Ooh, sulfur. 1 sulfur, but how many on this side? 1, but it's inside a bracket with there 3 sulfur. So how do I get 3 sulfur on this side? Simple. Put a 3 there. So now I have 3 sulfur. Next, all I have left are oxygen, hydrogen. I'll do hydrogen first. I could have done oxygen. How many hydrogen on this side? 2 times 1 times 3. In this molecule right here, there's 6 hydrogen. Now, if I go to this one, 3 times 2, ooh, same thing. 6 hydrogen. Let me get my calculator out. Not. Did I tell you my mother was an accountant? By the time we were 7, we were expected to add and subtract correctly. And if you went to Marshall Field's, now Macy's, the person who would write up your order, whatever you purchased, they didn't have the machines they have now or computers, and they had it in their head. And it was upside down. My mother expected us, or my sisters and me, to be able to add that faster than that and let them know when there's a mistake. She did too, and they did make mistakes. Anyways, back to this, 12 hydrogen. Oh no, 2 hydrogen. How do I get this to 12? Well, put a 6 there. 6 times 2 is 12 hydrogen. And then the only thing we have left is oxygen. I have 2 times 1 times 3. That's 6 oxygen. Ooh, 3 times 4 is 12 oxygen. And if I did my math correctly, that adds up to 18 oxygen. If I go on this side, notice in the bracket, I have 4 oxygen outside the number 3. So you multiply, that's 12 oxygen. And then here in water, I have 6. Oh, look, it adds up to 18. I think we did it. Let's do a final check. 2 iron, 2 iron, 3 sulfur, 3 sulfur, 12 hydrogen, 12 hydrogen, looking good. 18 oxygen, success, 18 oxygen. It's balanced. Victory. We did it. And that's how you balance equations. Remember, leave hydrogen, oxygen last. You could have done that first, but it would take you a lot longer and probably a lot more, how should I say, grief. Leave oxygen, hydrogen last, and also look out for even odd. All right, let's move on. Oh, I should point out on Thursday, the lab will be more balanced chemical equation practice for you, because it's a very important skill in chemistry that you should have. And as you learn by now, practice makes perfect. Everybody following that, what I'm doing? We already went through this. We did the balancing equation. I taught you what the coefficient is, but on a test, I'll never ask you what's the coefficient. All right, what I'm about to teach you next is probably the most powerful concept I know in all of chemistry. Again, it's the most powerful concept I know in all chemistry. Let's go back to this. And this is a balanced equation. Hopefully you can all see the whiteboard. I haven't used you guys today. Thumbs up, people. Can you see my whiteboard? Thank you. All right. What this tells us is we've got 2 hydrogen atoms, 1 oxygen. When there's nothing in front, it's the number 1, makes 2 water molecules. But it means much more than that. What? Let me show you. And that deals with chemical equations and the mole concept. And this is the most important thing I know in chemistry, one of the most. The coefficients in a balanced chemical equation give the numerical relationship among formula units, otherwise known as molecules consumed, what you start with, and molecules produced in a chemical reaction. So the coefficients in a balanced chemical equation give the numerical relationship, the molar ratios. In other words, the coefficients in a chemical equation or equation give the fixed molar ratios. This is so important, so powerful. Fixed molar ratios between substances consumed, in other words, used or starting with or reacted, and what you make. When we have a balanced chemical equation, well, this I already told you. And I've also mentioned that in any chemical equation, total amount of matter is equal on both sides, what you make and what you get. Again, notice I've repeated, the coefficients in a balanced chemical equation give you the relationship, molar relationship, ratios between the reactants and products. Let's take a look at what that really means. I know of nothing more powerful. What this really means when we look at this balanced equation, what's this? 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. And that relationship is so powerful. And maybe today or Thursday, I'll give you an example. But anything you purchase that's made with chemicals or includes chemicals like your soap, your shampoo, your fabric softener, your laundry detergent, different substances I call chemicals, you call ingredients in your food. Those are all that are made using this concept. The coefficient in front of a balanced chemical equation tells you how many moles, the molar relationship. 2 moles of hydrogen make 1 mole of react with 1 mole of oxygen, make 2 moles of water. How can that be so powerful? And let me decode this for you. How many moles hydrogen are needed to react with an excess of oxygen? That just tells you you have all the oxygen in the world to react whatever hydrogen can react with to make 12.6 moles of water. Well, what do? Well, we come over here and find out, what are we trying to find? Moles hydrogen. What are we given? 12.6 moles water. But you're given something else. Any problem like this, I would always include the balanced chemical equation. When I was an undergrad, the teacher would make you balance it first. I'm not that cruel. Don't tell anybody I'm being nice. Ruin my image around here. But anyways, how do we proceed? Oh, I haven't done this in a long time. It's time to use your good buddy, your good friend, unit analysis. Oh, I love that whistle. And it's time to use your good buddy, your good friend, unit analysis. How do you do that? You come over here and you only have one thing to start with. If I had a ratio, what units do I want my answer to be? Well, you learned that right here. Moles hydrogen. And now, how do you use your good buddy, your good friend, unit analysis? Whatever you're trying to get to goes on top of that ratio. Whatever you're trying to get rid of goes underneath. Well, I can do that. So on top, I have moles hydrogen. Underneath, I have moles water. And where do I get that relationship? From up here. For every 2 moles of hydrogen, how many moles of water do I make? And the answer is 2. Remember, the coefficients of a balanced chemical equation give you molar ratios. 2 moles of hydrogen, 1 mole of oxygen make 2 moles of water. Therefore, for every 2 moles of hydrogen, how many moles of water do I make? 2. Now, let me remind you, both of these numbers are exact numbers. Coefficients of balanced chemical equations are exact numbers and do not play a role in calculation. Well, let me get my calculator out now. And the answer here is 12.6. And this allows chemists to know how much of certain chemicals, and I'll teach you later on when you have to figure both of these, how to do that, but not now, how you use a balanced chemical equation to go from moles of one compound in that reaction to moles of another. Use unit analysis. This is what we had to start with, 12.6 moles of water. We're trying to find moles of hydrogen. Therefore, this is what I start with. The units over here are what I'm trying to get to. Follow the red arrows. Here, I put whatever units I want on top to be in my answer. Whatever units I don't want in my answer, I put underneath. Remember, I haven't done this in a while. Anything divided by itself equals 1. This cancels out. So we're left with moles of hydrogen, which is what we want. And then where do we get these numbers? From the balanced chemical equations. What's the relationship between moles of hydrogen, moles of water? For every 2 moles of hydrogen, you make 2 moles of water. 2 moles of hydrogen, 2 moles of water. I would give you this. And I could have also written it, how many moles chlorine are needed, reacting with an excess of sodium are needed to make 2.351 moles of sodium chloride. Let me do this one again. And then after the break, I'm going to let you try one because I like to share. So what are we being asked to find? Moles chlorine. What are we given? 2.351 moles of sodium chloride. We're also given the balanced chemical equation here. You can't do the problem without it, and I will always give that to you. In real life, you need one. So how do we proceed? Well, it's time to use your good buddy, unit analysis. And the only number I have and units is this to start with. Because once I have this, this is where all I have to look at. Now, initially, what do I want my answer to be in? Moles of chlorine. Because it asks how many moles of chlorine. That's what I'm trying to get to. And now I'll use my good friend, my good buddy, unit analysis. Remember, I'm going for the Guinness Book of World Record. Whatever I'm trying to get to goes on top of the ratio. Later today, I'll be practicing drawing arrows. But anyways, whatever I'm trying to get rid of, that looks a little better, goes underneath. So what does that mean? I want on top of this ratio moles chlorine. I want underneath moles NaCl salt, or please pass the NaCl. Where do I get these numbers in this ratio? From the balanced chemical equation. And when there's no number in front, that means the number one. And we're trying to see what molar relationship do you know between chlorine moles and sodium chloride moles? And the answer is, for every 1 mole of chlorine, we get 2 moles of sodium chloride. For every 1 mole of chlorine, you get 2 moles of sodium chloride. Now, before I pick up my calculator, moles of sodium chloride divided by moles of sodium chloride cancels out, because remember, A divided by A equals 1. So anything divided by itself is 1, or essentially cancel out. And now I can pick up my calculator. First of all, I got to open it. One of these lifetimes, I'll remember to have one set up where it's already formatted, but not today. All right, so if we go back and look at our whiteboard again, you'll see we want to divide 2.351 by 2. Remember, 1 and 2 are exact numbers. This is 4 significant figures. Our answer should be 4 significant figures. And this is what our calculator gives us. On test number 2, like 1, it will say, please use proper significant figures for all calculated answers. And I'll let you round that off to 4 significant figures. Time's up. Keep the 1, keep the 1, keep the 7, keep the 5. This 5 used to round off. Is that 5 or higher? Yes, it's 5, so it's higher. I drop that, and the zeros increase the number in front, so you get 1.176. And therefore, the answer to this problem would be 1.176 moles. If I look at the clock, I timed it just perfectly within about a few seconds. It's just about time for a break. Quick public service announcement. Don't forget to register. Don't forget to vote. I got my mail-in or vote by mail ballot yesterday. By the end of the week, I'll have it either. I'm going to see if I can find a drop-off box here at my city hall or somewhere. I will have voted. But remember, this is an important election. Don't forget to vote. I'll see you in 5 minutes. And I'm going to go stretch. All right, let's get started. Quick reminder, let me get you back about to start. All right, let me remind you, this Thursday, I'll be going through problem set 6 from the uh, Blackboard. Make sure you do it before I do. It'll help you do better, which is a good thing. All right, we're talking about balanced chemical equations, and the coefficient gives you the molar ratios between reactants and products. There's nothing more powerful, I know. Hold on, I dropped my notes on the floor. Got them back. And let's have you try one. All right, this one for you to do. And this balanced chemical equation, which you'll be given, shows you 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. It's balanced 6,622. So the question is, how many moles of hydrogen reacting with an excess of nitrogen, as soon as you see excess something, you can ignore it, are needed to make 1.73 times 10 to the third moles of ammonia? Your turn. Go. If you don't have a calculator, just try and set it up. What are you being asked to find? What are you given? And then use your good buddy, your good friend, unit analysis. Remember, I'm going for the Guinness Book of World Record, saying that the most times in a semester in a chemistry course. Hopefully I'm on track to win. Now we're getting into the juicy good stuff. When you're done, give me a thumbs up. I gotta call Zoom. They should have a thumbs down, meaning I'm not done. Remember, when you're done, give me a thumbs up so I know you're done. Or, okay, I see one person. Give you another 30 seconds, then I'm going to start. 35. All right, let's get going. And the question is, how many moles hydrogen reacting with an excess of nitrogen are needed to make 1.73 times 10 to the third moles of ammonia? So the first thing is, what are we trying to find? Moles of hydrogen. What are we given? 1.73 times 10 to the third moles of ammonia. And we're also given this balanced chemical equation. 1 mole of, remember the coefficient when there's nothing there is number 1. 1 mole of ammonia reacts with 3 moles of hydrogen to make 2 moles of ammonia, NH3. So how do I proceed? Well, this is the only number I have. If I had a magic ratio, it's not magic, it's chemistry. What units do I want to get to? Well, you took the time to figure that out. Moles of hydrogen. And it's time to use your good buddy, your good friend. I used the whistle enough tonight, so I won't give you a whistle overkill. But use your good buddy, your good friend unit analysis. Whatever units we're trying to get to goes on top of the ratio. Whatever units we want to get rid of go underneath. So I can do that. I want moles of hydrogen on top. I want moles of ammonia underneath. Where do I get those numbers? Well, I look at my balanced chemical equation and it says for every 3 moles of hydrogen, I make 2 moles of ammonia. Again, for every 3 moles of hydrogen, I can put that in, I make 2 moles of ammonia. Now, before I go, I'm going to check my units. Notice moles of ammonia divided by moles of ammonia cancel out because A divided by A equals 1. And now I'll get the right units. And now I'll go to my calculator, but just let me remind you, these numbers are exact numbers. And they play no role in determining significant figures. So this is 3 significant. My answer should be 3. And now I'm going to go to my calculator. 1.73 times 10 to the third times 3 divided by 2 gives me this number. And I'll let you round that off first to how many? 3 significant figures. Ooh, this is an interesting one. But this is real life, and it might happen to you on a test, so I'm going to let you have a little practice. Time's up. Let's take a look at this. You want to round this off to 3 significant figures. Keep the 2, keep the 5, keep the 9. Use this number to round off. Is that 5 or higher? Time's up. It's 5, so it's 5 or higher. This all gets eliminated or dropped. This number increases by 1. That gets you to 10, which increases this number by 1. So it's 2.60, 3 times 10 to the third. Wrong thing. Right thing. Everybody see my whiteboard now?
No.
Thank you, no people. Let's try it again because Zoom tells me it should be on there. Now do you see it?
No.
What?
No.
All right. All right. Zoom's being difficult. How about now?
No. We see this, but we didn't see when you did calculation.
Oh, I'm sorry. Well, let's go back to this. All right. Here's what this would be in this cell right here, A2. Now, can you see the spreadsheet?
Yes.
All right. When you don't see something, yell out, let me know. That's the one problem with Zoom. When I have things like this in share, they don't show me the screen that you see. I assume I see it on my screen is what you do, and it's not always true, which I've learned. All right, round this off to 3 significant figures.
$2.60.
Right, times 10 to the third.
Yes.
So let's go back. Now, does everybody see my whiteboard with the problem on there?
Yes.
Thank you. Thank you, Diana. And therefore, we come over here, and this would be 2.6 times 10 to the third moles of hydrogen.
In this situation, do you multiply or divide?
Both. This times this divided by 2.
Gotcha.
Because let's take a look at this. If you have this, this means A times B divided by C, okay?
Okay.
See, there's no such thing as a dumb question in my life ever, and my class too, which is part of my life. All right, let's do another one. But before we do, let's take a look at this reaction. I'll talk more about it later in the semester, but now would be a good time to fill you in on something. This is called the Haber-Bosch reaction because it doesn't show it here, but with a certain catalyst, and I'll teach you later on what a catalyst is, you take nitrogen gas, which you can get easily, hydrogen gas, I can get my hands on tons of it, I mean tons, easily, hundreds of thousands of tons, you make ammonia. Now, again, you take nitrogen, react it with hydrogen, you make ammonia. Well, it turns out ammonia is a very important chemical to have because with ammonia, we can make fertilizer. And the other thing you can make with ammonia is explosives. So this reaction, before they worked this out, If you needed fertilizer, you got it from your cows or other animals on your farm and spread it in your fields, which farmers were doing for centuries. But now, this was about 1910, 1908, farmers could get cheap fertilizer. And because you could get cheap ammonia, companies could make cheap fertilizer, farmers could get higher yields from their fields, and also grow crops on fields that usually they wouldn't have because they didn't have the fertilizer, and you had more food, and this allowed the population of our planet to increase greatly, and it did. Now, that's the good thing. The bad part of this is when there's good, there's always bad possible. Same reaction, cheap ammonia now available. Guess what? I can make cheap explosives. So now all the armies of the world could have bullets, rockets, artillery shells a lot cheaper. Therefore, they could have wars that were cheaper and last longer, which made World War I and World War II and other wars last a lot longer because they were cheaper to buy the ammunition to use in the wars. So with anything, there's always some good, some bad, and hopefully they cancel out. This is propane, which I'll never ask on a test, but that's the stuff in the white bottles you use for your barbecue. If you have a gas barbecue and you react it with oxygen and you make CO2 plus water plus heat, but we don't use that for balancing. Let me balance this. Three, 8, 8, 10, 6. All right, let's do this. Let's undo that. This way you can read what I'm writing. Slight mind problem. I got it right. I'm having a mental freeze. Let's do it this way. All right, let me decode it. First of all, how many moles of water are made when you react 15.61 moles of oxygen with an excess of propane, C3H8? You're also given this balanced chemical equation and use your good buddy, your good friend, unit analysis. Go. Remember, use your good buddy, your good friend, unit analysis, find out what are you being asked to find, what are you given, and then use unit analysis. Also, newer name, dimensional analysis, which I don't like. Good habits, Dr. White doesn't change. I was checking something on my calendar online, or anybody's calendar. And don't forget, when you're done, give a thumbs up or turn on your video and smile or do both or none of the above. All right, I think everybody's done. Anybody need more time? Yell out or give a thumbs up. Nope, I think everybody's, give you another 10 seconds. Bonus time, 11, 12, done. All right, let's take a look at this. What are we being asked? And let me bring in my balanced chemical equation, because we'll need it. We're being asked how many moles water are made. So this is what we're being asked. What are we given? 15.61 moles of O2. What else are we given? The balanced chemical equation. And that tells us 1 mole of propane reacts with 5 moles of oxygen to make 3 moles of CO2, carbon dioxide, and 4 moles of water. So how do we proceed? This is the only number we have to start with. I had a ratio. What units do I want my answer? Well, we figured that out here, mole of water. And now I made a mistake over here. Somebody should have caught me. I caught me. And unit analysis told me, you messed up. Because you can't start and end with the same thing. And here I have 15.6 moles of oxygen. Now I'm on the right track. And now I'm going to use my good buddy, my good friend, unit analysis. Whatever I'm trying to get to goes underneath, on top of the ratio. Whatever I'm trying to get rid of goes underneath. And now I'll write those in. On top, I want moles of water. Underneath, I want moles of O2. Where do I get those numbers? Well, I look up here and it says for every 5 moles of oxygen, I make 4 moles of water. For every 5 moles of oxygen, how many moles of water do I make? 4. And now notice moles of oxygen divided by moles of oxygen cancel out, because anything divided by itself equals 1. In other words, it's gone. And therefore, I'm in the right units. And now it's time for me to go to my calculator. And let's see if you can all see it. Time for a thumbs up, people. Can you see the spreadsheet? Thank you. $15.61 times 4 divided by 5. Before I hit it, notice 15.61, 4 significant figures. 4 and 5 are exact numbers, so our answer should have 4 significant figures. If I hit enter, this is what my calculator gives me, so I'll let you round that off first to 4 significant figures. Your turn. Time's up. Again, we're looking at this number, round this off to 4 significant figures. Keep the 1, keep the 2, keep the 4, keep this 8. This 8, is that 4 or less or 5 or higher? And time's up. Hopefully I'll pick 5 or higher. Therefore, I'm going to drop this in the zeros, increase this number in front by 1. So I get 12.49 moles, which now I can go back to my answer, my sheet, and know I would make 12.49 moles of water. And that's how you do it. And remember, find out what are you trying to get to? What are you given? You're also given the balanced chemical equation. And therefore, I start here. This is what I have. I'm trying to get to this. I use unit analysis. And where do I get these numbers in this ratio? From the balanced chemical equation. They're molar ratios. For every 4 moles of water, I need 5 moles of oxygen. That's where I got it. These are exact numbers, so you don't use those in determining how many significant figures. And that's how you do it. Now, there's one problem with this and what I'm showing you. There's a problem, and the answer is yes. If you go into the lab or anywhere else, can you find a device that measures out moles? And the answer is no, you can't. But you can find out a device that measures out grams. We call that a scalar balance. So let's look at the following. And now we're getting into what I call real life. Let me go down here. Yep, that's right, 10 points. And let's look at the following. And quick, because I've already had one problem when I assumed that I shouldn't. Everybody see the whiteboard now with the problem? Thank you. All right. How many grams of oxygen are needed to react with an excess of hydrogen to make 8.75 grams of water? And you're also given the balanced chemical equation. And it's 10 points. Well, what are we trying to find? Grams of oxygen. What are we given? I'm going to come down here. We're given 8.75 grams of water. So, and we also have our balanced chemical equation. I'm going to try unit analysis because you know that's been my good buddy and good friend. So, oh, by the way, this, don't copy. It even says it on the screen. I'll tell you why in a second. I have this amount of water that I'm given, and my good buddy unit analysis says if I have a ratio, what do I want my answer to be? Grams of O2. And now, since I know unit analysis, I'll put this on top, whatever I'm trying to get to. I'm doing it in red for a reason. And this underneath. And now I look around and find, where do I find a ratio of grams of oxygen to grams of water? And the answer is nowhere. I'm stuck. Where do I go on? Relax. Chemists found a way to do that, and let me show you. We did our practice time. For mass calculations for reactions, mass means grams. Finding the moles or mass in a substance that it comes in, this should really be grams. Or find the moles or masses, it should be just masses. You need 3 steps. You can't do it in 1 step. The first step, whatever you're given the weight of, you convert to moles. You learned how to do that already. Then the second step, whatever you now have in moles, you convert to the moles of what your answer should be. And the final step is, now that you have moles of your answer, you convert that into grams of your answer. So it takes 3 steps. And on an exam, and you can look in Blackboard, important information for test 2 is already posted. You will see this and this. It'll be given to you. In the past, I made students memorize this. Dr. White realized I'm testing chemistry knowledge, not memory ability. So I'm going to give this to you. Let's go back to our problem. So now I know I have to do 3 steps because this isn't going to get me there. Whatever I'm given in grams, I'm going to convert to moles. How do we know that? 1 mole of a compound, this will be given to you, but we already practiced this, and we'll be doing it again on Thursday with problem set for chapter 6. 1 mole of a compound equals its molecular weight in grams, and the molecular weight equals sum of all atomic weights. So what do I have? I have water. So in step 1, I'm going to go from 8.75 grams of water to moles of water. Why? Because step 1 tells me I go from grams, whatever I have, to moles, whatever I have. And now I'm going to use again, now I can use my good buddy unit analysis. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Moles of water here and grams of water here. And where do I get these numbers? 1 mole of water equals its molecular weight. Oh no, you've got to figure that out. How do you do molecular weight of water? You look at the periodic table. It has 2 hydrogen, 1 oxygen. And if you look at the periodic table, let's take a quick look. Hydrogen to 3 significant figures. On test 2, it will say underneath your name, please use proper significant figures for all calculated answers. Please use 3 significant figures for all atomic weights. Hydrogen is 101. Oxygen is over here. I'll let, excuse me, hopefully I didn't check. Everybody see the periodic table? Good. I'll let you round this off to 3 significant figures, and then we'll continue on. Excuse me, getting choked up on this oxygen. All right, that's 16.0. So I have 2 times 1.01, 1 times 16.0. These are exact numbers. So that's 202, 16.0. Add them up, 18.02. You get the same number of significant figures past the decimal as the number when you're adding that has the fewest. This is 1, this is 2. Therefore, this should be 1. Use that to round off. That's 4 or less. So for every 1 mole, I have 18.0 grams. And now I'll check grams divided by grams equal 1. I'm left with moles. So now I'm going to go to my calculator. Let's go to my calculator. And you should all be able to see that now. Anybody yell out if you can't. And now I'll come up here. Now 8.75 divided by 18.0, and this is the number I get. Now, this is going to be a multi-step calculation, and there's 2 mindsets when it comes to how do you round off. One mindset or one method is round off at every step. The other is wait till the end. Dr. White is a round off at every step person. However, I'm not going to force you into one way or the other. I will calculate both ways. Sometimes they're the same number, sometimes they're different. They're different both will be correct on the test. But let me show you how I do that when I'm doing a key. In column A, I won't round off till the very end. Column B, I'll do it at each step. Round that off to 3 significant figures, and you get 0.486. My calculator is going to throw in some zeros, ignore them. Now, we have 0.486 moles of water. And now we do step 2. Moles of A to moles of B. And what do? We look up here and say, I'm trying to get the moles of grams of oxygen. So that's my B. I've got already moles of water. So now I want to go from 0.486 moles of water. I want to get to moles. What do we want? Oxygen, because eventually we want grams, and that's our B. I'll use unit analysis, whatever I'm trying to get to. Come on, red pen. Whatever I'm trying to get to goes on top. Whatever I'm trying to get rid of goes underneath. Moles O2, moles water. Where do I get the molar ratio? From my balanced chemical equation. For every 1 mole of oxygen, I make 2 moles of water. Remember, coefficient when you see something is number 1. For every 1 mole of oxygen, I make 2 moles of water. For every 1 mole of oxygen, I make 2 of this. And now moles of water divided moles of water gives me moles of oxygen. And I go to my calculator. And here are my 2 answers. Column A, I'm going to wait till the very end. Column B, I round off at each step, 3 significant figures. That would be 0.243. Am I done? No. I'm going to go about a minute over. Hang in there for me, please. So now I put in 0.243 moles of oxygen. And now I need step number 3, where I want to go moles of B, in this case oxygen, to grams of B, which will be grams of oxygen. Why? Because that's what we're trying to get, grams of oxygen. So how do I do that? Well, I just figured out how many moles from step 2 of oxygen. I want to go to grams of oxygen. I'll use unit analysis. Whatever I want to get to goes on top. Whenever I get below, I want to get rid of goes below. And where do I get that number? 1 mole. Oh, look, somebody put it on the paper already. 1 mole of a compound equals a molecular weight. The molecular weight is the sum of all atomic weights. And therefore, I need the molecular weight of oxygen. That's 2 oxygen. Each oxygen, as we saw earlier, is 16.0. That's equal to 32.0. So for every 32.0 grams of oxygen, I get 1 mole. So 1, 32. This is an exact number. This is 3 significant. So I now know to multiply that. Before I do that, moles divided by moles oxygen cancel out. And now I go to my calculator. And notice if you round it off to 3 significant figures, you get the same answer. You don't always round either one of these to 3 significant figures, and you get 7.78. Sometimes they're different. I'll write it again, 7.78. And that's how you do it. And I'm out of time. Wow, I timed that just to the second. I'm out of time. It's time to go. Remember Thursday, do chapter 6 problem set. Wow, what am I going to do when we get to chapter 12? But anyways, hold up a piece of paper with the number on it. We'll do chapter 6. We'll also be doing the new lab. Don't forget the lab you did last Thursday is due this Thursday by, I think, 5 p.m. I have it set up so you don't get any penalty points. And with that, I'm going to say bye. Gang gesund, be healthy. Or as Granny would say, bye.